I take great pleasure in introducing the next speaker, Dr. Srinath. Dr. Srinath holds a PhD from the Berlin-Brandenburg Graduate School for Distributed Information Systems, Germany, an MS by Research from IIT Madras, and BE in Computer Science and Engineering from the National Institute of Engineering, Mysore. He works in the areas of web science, multi-agent systems, network analysis, and text mining. He is a member of various technical and organizational committees for international conferences. He is also a life member of the Computer Society of India. As part of academic community outreach, Dr. Srinath has served on the Board of Studies of Goa University and as a member of the Academic Council of the National Institute of Engineering, Mysore. He has served as a technical reviewer for various journals like the VLDB Journal, IEEE Transactions on Knowledge and Data Engineering, and IEEE Transactions on Cloud Computing. He is also the recipient of various national and international grants for his research activities. Currently, Dr. Srinath heads the Web Science Laboratory and is a founder member of the Center for Data Sciences at IIITB. Dr. Srinath will be giving a talk on towards mathematical foundations for social machine.
Good afternoon. I do realize that I'm standing between you and lunchtime, and so let me try to make my talk slightly partly philosophical and partly mathematical. That's what I do for a living, actually. So as you all know, I head the web science research initiative here, and the idea of web science, the term web science was coined by Tim Berners-Lee in about 2006 or so to represent scientific activities to try to understand how the web is shaping our world, so to say, right? And so it's not about technologies for building the web, but about understanding how the web is impacting us. And so web science is a very interdisciplinary study. So you see in the web science annual conference, you see a lot of political scientists, you see a lot of social scientists, psychologists, and linguists, and so on, including computer science, right? What I would like to do in this talk is to show that web science does have very strong mathematical problems at its core. And there's a lot of work for us mathematicians and theoretical computer scientists and engineers to do. Some of these problems basically address the core of effective computing itself, what we can do with computing and so on, right? And sure, at the one end, web science is very applied, and we can see its impact directly, but there are also very deep theoretical questions that we need to answer if we have to get any answers to our questions. So let me start off like this. In order to understand the web, we need some kind of a model, right? We need a paradigm, right? What is the web? Okay, and our understanding of the World Wide Web has evolved over the years very drastically, right? So in the 90s, when I first attended the first World Wide Web conference, the biggest computer science research at that time was dominated by advances in database technology, right? And so people were trying to fit the web as a database. So is the web a large database? And they were basically looking at the web as some kind of a ill-behaved database. Okay, there's no schema for this web. It's unstructured, and so unstructured data was seen to be the biggest problem, right? But we have thus far evolved away from that, and we know that web is not just a database. I won't go into the reasons why, but further on, the next biggest paradigm that came into picture was the web as a repository or as a digital library, right? So digital library is much less structured than a database. There are so many books and so on. So you have, for databases, you have notions of query and schema and so on. For digital libraries, you have looser notions like, say, ontologies. And retrievals and so on, instead of actual SQL queries, and so and you have a notion of relevance, and so that's where information retrieval and such kinds of background started coming into the web, right? Then came, of course, as we all know, Google and PageRank, right? So till this time, what people were doing were basically focusing on the content in the web. Okay, so they were just looking at the text and the kind of structure or lack of structure and so on. Hardly anyone had noticed that the hyperlink structure in the web has very rich semantics to it. right? So hyperlink is placed by someone for some reason, so you can actually interpret the hyperlink in some way and so on, right? And so that is when Google, for example, Brin and Page came out with their PageRank algorithm. But of course, they were not the only ones to do that. Kleinberg and others had come out with their own algorithm called HITS, which is also very well known. And so what they tried to do is, and of course the roots of this was traced back to the beginnings of hypertext, Fanefar-Bush's paper called As We May Think, right, where Fanefar-Bush had mentioned that he had proposed a machine called Memex, which was very similar to today's hypertext. And basically his argument was that this is the way we think in our brains, and organizing information in this fashion is a cognitive extension of ourselves. Okay, so just like all technology is an extension of ourselves, right? So a binocular is an extension of our seeing abilities, a mic is an extension of our speaking abilities, and so on. And the web was seen as a extension of our thinking abilities, right? Cognitive extension. Right? But we have now evolved beyond that as well. And in fact, this is perhaps the most current understanding or paradigm of our web, that the web is not a technology, right? It is not an extension of ourselves. In fact, we are an extension of the web. Okay, so we are not using the web is using us, right? And so we are not users of the web, we are participants in the web, right? So the web is no longer a technology, it's a space. Right, it's a space where we live, right, where we reveal ourselves, okay, and get used by others, okay, and we use others or whatever, right? And so it is not just a technology at all. And so this paradigmatic shift from a technology to a space changes the whole picture, or changes the whole question, right? And so that is the idea here. So this is the most contemporary paradigm for understanding the web. So earlier we were looking at the web like this, that the web is here and we are here, but now we are inside the web, right? And we are part of the web, and we have our sense of identities at different places in the web, and we are constantly molded by what we reveal, and we are constantly molded into revealing things, whether we want it or not. And right, and so and of course we are very much participants. So we are not. We are no longer users, right? And web uses us as much as we use the web. And the shift is now, so the emphasis is now shifting from retrieving information. So Google and Yahoo are no longer web search companies. They're no longer interested in retrieving information from the web. They're more interested in engaging users with the web. Okay, they are no longer interested in the web, they're interested in you. Right, and how they can get you to participate in, which is why, for example, a company that was bought for $19 billion, WhatsApp, okay, is giving its services for free. I mean, where does the 19 billion go, or how does the so it seems to the mathematics doesn't seem to add up, right? And you see that lots of such things are becoming more commonplace. Crowdsourcing and participatory authoring, e-tailing and so on, right? So now our question is now this thing. Okay, so now that we have a space, okay, it's an abstract space. It's not a physical space, right? What are the building blocks in this space? To also ask another allied question, in the early days of the web was primarily relegated to educational institutions, .edus, right? And free speech was taken for granted in some sense, right? But then came the .com boom in the mid-90s, and suddenly the web, which was up till now was seen as a academic platform or a learning platform, suddenly was seen as a marketplace. Right? Now the same platform, when you see it as a marketplace, your priorities change completely. Right? Now you needed security, transactional security. You needed things like authentication and credential check and digital signatures, all kinds of things. Right? And today the web is primarily seen as a political platform as well. Okay, or increasingly being seen as a political platform where political correctness and a lot of other things are also taking precedence, and which can have conflicts with free speech and so, right? And so there are lots of these issues that are coming up and intermixing together and so on. Now our question now is, what does this space contain? Okay, what are the elements in this space? Okay. Yes, please. Yeah.
Very interesting hypothesis that you are raising, but it seems to me that every change has been the result of some innovation in
Correct, yeah.
Google with its
Right, yeah.
WhatsApp, or it was because of advances in cryptography and RSA.
Right. Yeah.
So it seems that it depends on what input we are giving into the web.
Sure, very much. Yeah, so it is an emergent characteristic. Right. Very true. So it's not. The very important point made here is that the web is not found in nature, right? It's a result of our activities, but so disparate activities, okay, taken in disparate contexts, suddenly they're interfacing or interacting with one another, right, and resulting in a phenomenon, okay, which is now coming to have its own characteristics. So that's the this right. Let me introduce another concept now, which is central to this talk, the concept of social machines, another term coined by Tim Berners-Lee, which are now seen as the elements of this global socio-cognitive space, right? So the web is not made up of pages and hyperlinks anymore. In fact, the web is now seen as a network of social machines. Okay, so what is a social machine? Social machine represents a class of environments comprising of interplay between humans and technology, and whose emergent characteristic is a result of both human and algorithmic decisions. So both are influencing each other, right? And the web is basically seen as an engine to create abstract social machines, right? So we can create social machines on the web, we can deploy them on the web, we can make them, we can manage and interact with them and so on. Now basically our focus is now shifting to, can we characterize a social machine? Okay, so what can a social machine do? What can it not do, and so on. Okay, so we are going to look at it from a computer sciencey perspective in terms of what is the expressiveness of a social machine, right? And okay. So let me just give some examples of social machines. I'm sure many of them are familiar. All of you are familiar with Wikipedia, Twitter, Facebook, and so on. Truecaller, I'm sure many of you have used, right? So as you can see, Truecaller claims to tell you where is the number coming from, when on your mobile phone. And how does it do that? The thing is, where does it get its database from? It gets it from you. That is, when you become a part of Truecaller, you share your address book, right? So you're no longer a user of Truecaller. You're a participant. You're a contributor to Truecaller as well, right? And same thing with Quora or whatever. We are the content. Okay, we are not the customers of Quora, right? And so on. So there are lots of such social machines around. Waze is one more which I'll probably focus on. How many of you know of Waze? So Waze is basically a collaborative traffic management system. So if you download Waze on your mobile, you can actually send out the information about whether there is a traffic jam somewhere, slow moving traffic. You can ask for a ride, you can you can call for a ride, all kinds of collaborative management of traffic in this, right? And so it's quite popular worldwide, and even in India there are quite a bit of users around. And Ushahidi is one of the biggest success stories coming from Africa. I think Kenya in Africa, where it's a social bookmarking engine where people can point out where there are riots happening, right? And so it has been deployed in several cases where there have been conflicts, so that you can crowdsource things about where are riots happening, and so, right? So now the question is, what is the expressiveness of all of this? How can we characterize? Is there a mathematical foundation for all of this, right? So what we'll do is, we look at it in two ways. I mean, if time permits, I'll go to the second one, but I'd like to really focus more on the first part. Okay, the first part is the philosophical expressiveness of a social machine. What mathematically, what can it do, right? And how do they compare with effective computation? The Church-Turing thesis, right? And I'll also talk about some things that we have done in this area and validation primitives and so on. The second is about the mathematics of building a social machine. So if we take an abstract architecture for a social machines, what are the challenges that we encounter at different layers in this architecture, right? And so I'll just give a brief overview of both. Okay, so let us start with the holy grail of computing. Okay, the Turing machine. So Turing machine is seen as the mathematical model for effective computation. So the Turing machine basically represents an algorithm, mathematical model of an algorithm, and then the so-called universal Turing machine represents the mathematical model of a stored program computing. So every and the Church-Turing thesis basically states that any computable function is effectively computed by a Turing machine. Okay, or other similar Turing complete models like, say, lambda calculus and first order logic and so on, right? And so there are a lot of similar. So what does a Turing machine look like? So it basically has a state space, okay, and an alphabet T and an infinitely long tape, right? And it starts from a starting state, and at every state, what does it do? It just reads the element on the tape. Okay, depending on what state it is in, it performs, it optionally writes back something on that, and then moves one step to the left or right. Okay, and that's all. Okay, and it keeps computing that till it reaches any state in H. That is one of the halting states. So if it reaches there, it halts. Otherwise, it just keeps computing. And so that's the simple model of a Turing machine. But what we are interested in now is this one little thing over here, right? The little thing here is that from the moment a Turing machine starts computation, okay, to the moment it halts, it basically shuts out the entire world, outside world, right? So it is basically an atomic transition between the start state and the end state, right? And among other things, what it also means is that you cannot change the problem statement after you have given it to the Turing machine, right? So you give a problem statement to the Turing machine, and it just shuts off the world, computes an answer, and gives you the answer. You can't interfere in between, right? And how do we express the how do we represent the expressiveness of a Turing machine? It's also called as a recursive and recursively enumerable set. So we talk about the language of a Turing machine. So if I have a alphabet and a universe of discourse, that is the set of all strings that can be generated from this alphabet, the language is of a Turing machine can be represented in two ways. What is called as a recursive language or a decidable language, where for every element in this UOD, the Turing machine either halts and says either a yes or a no, right? So it either recognizes the string or does not recognize or derecognizes the string, right? And then there are what are called recursively enumerable languages, okay, where all that we say is that all valid strings in this UOD are recognized by the Turing machine. So there's nothing said about an invalid string. So for an invalid string, a Turing machine can either say no or may not halt at all, right? And so at least, but you should be able to enumerate all all valid strings in this, and generate this language and so on, right? And so R and RE sets are basically seen as the limits of computability, and in set theory, Georg Cantor's set theory, they belong to this infinite class of set called Aleph naught. Okay, so they're the smallest infinite sets. Okay, so Cantor was one of the pioneers in set theory who showed that there are an infinite hierarchy of infinite sets, each one of them provably bigger than the lower in the hierarchy and so on, right? So there are sets called classes of sets called aleph naught, aleph 1, aleph 2, and so on, and you can actually show that every aleph k is strictly bigger than aleph k minus 1, even though both of them are of infinite size, right? And so that's and what we know as computation is at the lowest level in this hierarchy, aleph naught. Okay. Now let us try and get back to this little thing that we saw, the closed world computation in Turing machine, right? Now look at any social computation that happens. Okay, so I'll take some very simple example. Okay, let's say you have the problem of driving home from work. Okay, so you start from work, you drive home, so you have a destination, right? So there is an end state, you have to reach there, and what is the biggest problem? The biggest problem is you don't know how the traffic is, or you don't know what kind of obstacles there are. You can compute a path, but you still have to drive through the traffic. Okay, now let's assume that theoretically we know where all the vehicles are, or where each and every obstacle is and how are they moving, and we can compute a model for each and everything that we are going to get and feed everything a priori to the Turing machine. Okay, so now can I make a closed world transition? That is, can I build a robot which can go from here to home without completely shutting off the outside world? Okay, the thing is, the answer is still no. Why? Because the outside world may change because of your actions. If there's a robot rushing at you blindly, okay, even though you're going in some way, you might change your. So there's no way for us to basically compute the complete state of the environment and provide it a priori, right? And so there's an interleaving, somewhat like the Heisenberg's uncertainty principle in quantum mechanics. Just like our task of measurement can change the system, our task of computing can even affect the system when you're actually computing and so on, right? And I'll come to this. So in the late 90s, there was a Brown University professor called Peter Wagner. He coined this term called empirical computing, right? So to talk about computational problems which are open world in nature. So this is a closed world Turing machine computation where you give an input and you shut off the world and you get an output. Okay, but this is what is called as a single stream interaction machine, where you give an input, it gives an intermediate output, you give another input, it gives an intermediate output, and so on, right? And the thing is, this intermediate input here may be dependent on what output you get. So you may not be able to give all the inputs a priori to begin with, right? And but then in terms of observable characteristics, right? If you give the same input again and again and again, your outputs may be different. Okay, why? Because it is not starting from the same start state every time, right? So this is what is called as a hidden variable system. Okay, hidden variable computing. Okay, but the kind of social machines that we are looking at are even bigger than that. That is, there is a system. Let's say this is the algorithmic component of our system, and it's interacting with multiple users or participants on different interaction channels simultaneously, right? And there is a persistent common internal state that is getting that is getting impacted by every interaction, right? So for example, this guy gives an input, he gets an output here. By the time he gives an input, there is another transaction that has happened here that has changed the internal state, right? And so even though he knows what is the history of previous inputs, it would appear that its output is non-deterministic and so on, right? And so this is what we call as a hidden adversary machine. So there seems to be hidden adversaries for every input channel, which is impacting this whole process, and so, right? And Wagner wrote a pretty provocative paper saying that these are richer than Turing machines. Okay, so richer in expressiveness than Turing machines, and of course you can imagine that it caused quite a bit of controversy because Church-Turing thesis is quite widely established and widely used as the basis of the foundation of computing. And of course, there were no clear proofs, okay, as to what how that this is really more expressive and so on, right? In order to provide a proof, it's basically this is where we know of uncomputability. That is, we know that the set of all Turing machines, okay, form a countably infinite set. Okay, while the set of all languages over a given UOD is the power set of a countably infinite set, which can be shown to be strictly bigger than a countably infinite set, strictly bigger than Aleph naught, right? And this is given by Cantor's famous proof called the diagonalization argument, which I won't go into here, but which can precisely show that the power set of an infinite set is strictly bigger than the infinite set. You can't have a one-to-one mapping between the set and the power set and so on, right? So this showed the existence of uncomputable functions because the total number of languages are uncomputable, and defining the limits of effective computation. And further on, there were a lot of specific examples of problems which were shown to be uncomputable. Okay, most famous of them are the halting problem, which is very well known. That is, if I give a Turing machine and an input for the Turing machine as an input to another Turing machine, can this other Turing machine determine whether this Turing machine will go into an infinite loop or not, right? And in the general sense, this is shown to be an uncomputable problem. Similarly, program verification, or even simple things like integer roots of an arbitrary polynomial, okay, are shown to be uncomputable, right? So there are specific examples of problems that we know that we cannot write an algorithm, right? So if somebody claims that let's say an interaction machine is more powerful than a Turing machine, then they'll need to show how can you solve the halting problem using an interaction machine, right? So what I'll do is I'll just partially answer this question and take further, because there are so many open questions over there for which we still don't have really good answers, and especially when you relax the closed world argument in this case, right? And so basically social machines are open world processes, and there are essentially three elements to a social machine. So there is computation, Turing machine like computation, there is persistence of state across computations, right? And there is what is called as channel sensitivity, right? Which channel you give. So it is not only important what you compute and what answer you give, but it's also important to know where you give the answer and so on, right? And there were some, but then did Turing himself know about this? Okay, here is another interesting tidbit, okay, from Turing's own paper from the 1936 paper on computable numbers and the Entscheidungsproblem and so on, okay. What we now know as Turing machines, okay, are what Turing proposed as A machines, okay, are also called automatic machines, right? And so this is what we now call as Turing machines. And but Alan Turing also had proposed two other machines, okay, which are kind of forgotten in the paper. One was what is called as the C machines, or what are called choice machines, and another what's called as O machines, oracle machines, right? And he did not develop these models further, but what choice machines could do is that in the middle of computation, whenever they reach a state called a C state, okay, they'll accept changes to the tape from the external world. So the external world, a human can come and change the tape, and then it can continue computation per se, right? This is exactly what we are looking for, right? Where in an interaction machine, and in an oracle machine, the Turing machine is permitted to consult an oracle, which is not a machine, as part of its computation, right? So if I want to give an answer to something and I can't answer this within my state space, the oracle can come and change the state space, that's all, right? And Turing basically said that these two could be more expressive than this, but he did not develop the model further, right? And so that's an interesting tidbit from his original paper itself. Okay, so let us look at hidden variable machines to begin with. Okay, hidden variable machines are not all that bizarre as they look like. Okay, they have been studied quite quite extensively. Okay, most importantly in the field of reactive systems and distributed computing, concurrent computing. There's a lot of hidden variable systems that have been proposed. Okay, so for example, there are models that exist like labeled transition systems. Okay, which are potentially infinite state spaces. Okay, where a computation is seen as a trace in the state space. Okay, so the computation can start anywhere in the state space and end up anywhere else in the state space, right? And researchers like Manna and Nueli, have basically stated that the problem of reactive systems is characteristically different from the problem of algorithmic computing or Turing machines. Okay, why? Because Turing machine computation essentially requires you to stop before you say that you have computed something. Okay, so a function is a mapping from problem to a domain, from a domain to a range, and you have to stop this computation before you can start reasoning about it, right? And but a reactive system is a system that is meant to maintain an interaction with the external world. So you never stop. Okay, you stop only when you fail. Okay, so to give an analogy, it is like as biological creatures who are fighting for survival, when do we know that we have succeeded in our fight for survival? We never know, right? Have I survived now? I don't know, maybe next moment I can die, right? We only know when an organism has failed in the fight for survival, right? We never know when it has succeeded, right? And so because maintenance is not a problem with an end. Okay, it is a continuous problem, right? And basically they were showing that this kind of problems are not characterizable by Turing machine mappings or expressiveness, right? In 2004, Goldin and others, Goldin was a student of Peter Wagner, they proposed something called as a persistent Turing machine, which we can show to be equivalent to an LTS and labeled IO automata. So IO automata was created in the context of distributed computing by Nancy Lynch and others at MIT, right? And so what a PTM does is it's just like a Turing machine, except that it has a persistent tape. Okay, and it basically starts computation after referring to the contents of the persistent tape in addition to whatever inputs you give. Okay, and here we'll show one little proof about expressiveness of a hidden variable machine. So let us say I have a persistent Turing machine, which is a universal Turing machine, and let us say I give it as input a Turing machine specification, a normal Turing machine specification, and an input string. Okay, so just like any other Turing machine specification, I take. Okay, then what does it do? It checks in its persistent tape whether Tm comma W has already been provided as input. Okay, if so, it does not do anything. It will just finish computation, or if not, then it will simulate Tm for W and provide the output. Okay, and record that I have simulated Tm comma W. Okay, and so on. Okay, now see what is happening here. Okay, what is happening here is that what the PTM is doing is that it is generating a power set of all Tm comma W pairs, right? It is generating some arbitrary subset, and every time you run, the language of this PTM is basically the power set of Tm comma W. And note that we have not required the PTM to stop as well. Okay, in a reactive system, you are not even required to stop, right? So it could be an infinite subset, right? So there you go, right? So basically, what we did is we basically simulated the power set of a countably infinite set, right? And which we know to be bigger than Aleph naught. Okay. So yeah, I know you're not completely convinced with the proof that the expressiveness of PTM is bigger, because of course there are caveats. Okay, so one is this proof. Yeah.
You only see the output when the computation is complete, right?
That's the that's the caveat also here. That if we take the reactive machine analogy as well, right? So in a reactive machine, you're not required to finish computation. So once we accommodate that here as well, then you can have infinite subsets, right? And so that's the caveat. right? And this accommodates infinitely long interactions, okay, with the external world, okay. And of course, this proof does not give us any empirical insight. That is, for example, can I use this to solve the halting problem? Okay, I still don't know, right? So we just showed that it can generate the power set of a countably infinite set, right? Now this is about just hidden variable machines, okay? And when we come to hidden adversary machines, things get even more complex. Okay, now the thing is, with a hidden variable machine, you are interacting with a single interaction stream, right? With a hidden adversary machine, there are multiple interaction streams, each one interfering with one another. And there are some well-known results in Turing machines. For example, so these are hidden adversary machines. So I think I can go to, okay. So in Turing machines, we know that a multi-tape Turing machine can always be reduced to a single tape Turing machine. Okay, there are strict or clear proofs of reducibility of a multi-tape TM to a single tape TM. But there are strict proofs again here to show the irreducibility of multi-interaction or multi-stream interaction machine to a single stream interaction machine. A multi-stream interaction machine cannot be reduced to a single stream interaction machine. And I'll just give an idea of the proof. Okay, so the proof comes with the fact that the response has to be channel sensitive. Okay, so let me give an analogy for this proof. Okay, you all know the problem of how to play chess with two grandmasters and win against at least one of them. Okay, so how do you do that? So there are two grandmasters. You see what move this one makes, you go and make this move here, and you see what move this one makes, and you go and make that move there, right? And so you're actually playing them against each other. Right? Now you see these are two interaction channels, right? So you can't reduce them to a single interaction channel. Because there is a dependency between the channels between these two, right? And so basically a multi-stream interaction machine cannot be reduced to a single stream interaction machine, right? But we still don't have any good models of what is the expressiveness in terms of the language and so on, right? Is this going to be even bigger than aleph 1 or 2 power something? We don't know actually, and I suspect that the continuum hypothesis will come into the picture here as well, right? Because we know that it's not as big as the power set of a PTM, okay, but it's somewhere in between. Now, is that in between bigger than this one or not, can be answered by this so-called hypothesis called the continuum hypothesis, which is still a open problem with in Cantor's theory of hierarchy of infinite sets, right? And so this is about the expressiveness. So what we did in our work in our lab some years ago is to try to ask, okay, let us not ask about the theoretical expressiveness of a multi-stream interaction machine, but instead ask how can we validate a hidden adversary machine model. Okay, what kind of validation primitives do we need, right, in these things? And so that is where we started proposing some kind of a model checking mechanism for hidden adversary machines, right? And so this was a proposal. This is slightly more advanced than the publication which we made in 2007. So the first thing what we did was, so we need a model to understand the multi-stream interaction that's happening, okay, in a social machine, right? So for that we proposed a model called the interference schema, right? So the interference schema basically captures, in some sense, how is one participant's activity interfering with some other participant's activities, right? So how do we do that? We take a state space of the entire machine, which could be infinite for all we know, just like a LTS and so on, and there's a possible set of transitions between states. Okay, now except that this state space and transitions are not executed by one machine, but by multiple participants simultaneously. Okay, in a non-isolated fashion. Okay, so so the P is a set of participants. Okay, and W basically maps participants to states, so which basically forms what is called as a configuration at any given point in time. And psi is a set of interferences that one participant being in some state may pose a constraint on some other participant being in some other state, and so on. Okay, and we developed a very simple interference model. But before that, one more small thing to note here is that until now, whenever we talk of machines, state machine and so on, we kind of equate the state space with the machine itself. Okay, we say that the machine is in this state, machine is in that state, and so on. Okay, but here we should see that in a hidden adversary system, computation is now happening in two levels. Okay, one is the algorithmic level, which is the machine itself, which is doing the computation. The other is the activities of the participants. Okay, so my participation in a social machine is changing the algorithmic state of the machine, but its responses to me is also making me change my strategies or change my right. So that's the idea here. That is the transitions in a in this hidden adversary machine or social machine or whatever, right? Is partially determined by the algorithms, by the machines, and partially determined by the strategic capability of the participant. Okay, to give a very simple example, suppose the shared state space is a geographic area, right, and where the states are the different locations. Okay, now state transitions are determined by terrain constraints, that is whether this location is adjacent to that location, can you go there. Okay, that is one, so that is determined by the machine, but it's also determined by the participant. Okay, so if the participant is a boat, for example, okay, now two islands are adjacent. Okay, but if the participant is a car, okay, then these two islands are not adjacent, and so right, and so it's partly, state transitions are partly determined by the terrain, which is the machine, and the participant, right, and so the computation is kind of split in between these two, right. So then we proposed a very simple constraint model. And we are not claiming that this is the only constraint model possible, but just for sake of simplicity, we did like this. So what we did is each constraint looks like this. Okay, you either give a S or a not S somewhere here in the antecedent, and in the consequent you have a constraint M applying to this state. Okay, so this means that constraint M applies on state S if if S1 is occupied. Or if negation is true, then if S1 is free, and so on, right? So, so for example, something like this means that if there is somebody in S1, then there's no entry to state S. That is, the entry to state S is blocked. Okay. Similarly, it says that if there's no one in state S1, then exit from state S is blocked. Okay, so we're just having two constraints. So an entry constraint and an exit constraint. Okay, so you can't enter here or you can't exit from here, right? Now, then. Of course, one more small caveat here is that you cannot interfere with yourself, right? So if I have a rule like this, S gives no exit S, it means that if state S is occupied, okay, then I cannot leave the state S unless somebody else enters state S. Right, so that's the idea here. So this specifies a live lock condition in this, right? And, so now what we do is we look at the entire state space and we look at specific configurations in the state space. So configuration represents a mapping from participants to states, right? And so we have a finite set of configurations of interest for us, okay, to observe, okay, and then we say that there is a valid transition from configuration W to W prime, okay, if for example the transition from W to W prime involves a set of constraints such that there is no causal dependency between the constraints. That is, one is they're all concurrently imposed constraints on one another, right? And of course, no constraints are violated from between these two. Okay, so this is the setup. Okay, now what are we observing? Okay, what is it that we are validating for? Okay, so for that we introduced another new concept. Okay, yeah. Before that, of course, what we look for, of course, is a trace like this or a walk. configuration, so W1 to WK, and we basically reason on this trace, okay, do some reasoning on this. So what we are looking for is this concept called collusions, okay. So collusions, this concept also comes from, I should probably introduce this other term, there is this notion called adversarial theorem proving. Okay, first introduced by Fisher, Lynch, and Patterson in the concept, in the context of distributed computing, distributed consensus. Okay, so this is the systemic equivalent of proof by contradiction. Okay, so what does this do? The thing is, suppose I have a system in place, okay, and I know that, and a protocol for the system, and I know I want to say that this protocol works. Okay, how do I do that? I assume that there is an adversary who is trying to foil your protocol. Okay, in your open world, right? So you're traveling from, you're driving home from work, and there's an adversary whose goal is to stop you from reaching home, right? Now the question is, what capabilities should the adversary have to successfully foil you? Okay, now if I can show that such an adversary is impractical to exist, okay, then I know that this I have basically validated my protocol itself, right? So that's the idea here. Okay, so what we are doing here is, we are not looking at one adversary but collusions of adversaries, right? And we see that collusions are really the biggest problem in a lot of social machines, right? There is something called as click attack for PageRank. You can increase your PageRank by creating a click of pages which are connected to each other and so on. There are mobbing problems in IMDb which have been reported, or for example, collusion among motorists to circumvent traffic rules, speeding rules and so on. So Waze is often used by motorists not just to beat the traffic but also beat the traffic rules. So to say that, okay, this part of there are no policemen here, you can speed or whatever, right? And so there are a lot of collusion that are possible in social machines. So we introduced this notion called a collusion number, right? So a collusion number is basically the smallest number of participants that is required, a collusion number and a given configuration, let us say, okay? So given a social machine and a given configuration, okay, what is the smallest number of participants that are required to guarantee either the existence or non-existence of W in any arbitrary trace of this thing, right? That is, what is the smallest number of participants necessary to ensure that this machine will either guaranteedly reach this configuration or will not reach this configuration, right? So which means they're gaming the system. What is the minimum number of participants required to game the system, right? And here is one example. So suppose I have three states like this, S1, S2, S3, and then there are some constraints. That is, S3 says, there's no entry to S2 as long as someone is here, and S2 says there's no exit from S3 as long as someone is here, right? You can think of this as some kind of a protocol where you enter, immigration or security check or something like that, right? Where you have to go from S1 to S2, finish validate yourself, and you go to S3 and get out and so on. Okay, but if I have a participant with a capability of S1 to S3, going from S1 to S3, I can see that with just two participants, I can effectively prevent anyone from ever entering S2. Right, by one going here, staying here, and then another one here, waiting till he comes here and goes off. So the exit from S3 is always open, and the exit entry to S2 is always closed, and so on, right? And so this is the kind of model that we introduced. So you see, we are looking at model checking from a lateral perspective. So we are not looking at transitions themselves, but we are looking at constraints. And say, now that I'm here and I'm posing a constraint elsewhere, what can I do, or what can't I do? So right, and so this was what we proposed in 2007. After that, I have not got any more student to work on. This was the work of my first PhD student. After that, we have not had any more to work on this. But so let me kind of they already hinted to me that my time is up. So let me skip the part 2 part, okay, which is more empirical, and essentially talk about the idea of collusion number, okay, or the notion of collusions being the basis on which we can have a formal model for the construction and operation of social machines, and you can probably think of validating social machine architectures just like we do model checking on hardware and so on. So that's the that is the potential outcome that we are looking from this, right? And so let me kind of skip all this and semantics. I had quite a bit of right, and so anyways, I'll just conclude by saying it's a very exciting research area, fostering the so-called empirical computer science, or basis for empirical computer science, and there are lots of open problems here, okay, when we combine constraints with transitions, and we are not even started to talk about social, psychological, political aspects of the web and so on, all of which are also part of web science, and I'm just talking about the expressiveness of social machines which make up the web, right? And there are pretty deep problems inside. So let me stop at this note. Thank you. Should we take questions? Yeah. I think.
So there is this related area of cyber physical systems, which looks somewhat similar to these social machines that you're talking about, in the sense that we have this computation of elements and then they're interacting with intelligent decision-making agents. So it would be nice if we could kind of relate these two.
Definitely, I'm not completely aware of this field, but I'm assuming that a cyber physical system comprises of a single human and a single machine interacting. It's a man-machine complex, or does it comprise of multiple humans and multiple?
For example, a smart grid.
Okay, yeah. Then there, in some sense, the social machine, the idea of a social machine that we introduced here. So it is just an ensemble. A social machine is an ensemble of humans and algorithmic components, and the property that we see is an emergent property of both.
So there, a fair bit of success has been achieved in mathematically modeling them, or the components of such machines or cyber physical systems, and then doing analysis on top of that. Manoj's talk, the one just before yours, was kind of an example of that.
Okay, I'll look into that. I'm not sure, are they looking into constraints and interferences like the way we talked about, and because that's the focus of our work, at least in this. We have seen a lot of work that talks about reachability, or transitions, or and so on. But what about constraints or unintended interferences from other machines? And given that, how can we validate modeling? So that was the primary idea in this. I think Amit had a question.
You started with saying that technology is an extension of human beings. Then you said social machines, and responding to this, it's an ensemble of humans and
technology.
I just wanted to understand, are there technological elements which are not social machines?
Suppose I would. Okay, let me take us let's take something like a binocular or so on, right, which is used by a human. Okay, so sure, there is a interaction between human and technology in that sense. Okay, but the definition of a social machine is not that. Okay, the definition of a social machine is a society of humans where whose emergent characteristics are a combination of both human and technological decision making. Right? Sure, there were always there all over the world that sure we had some we use some technology like paper or writing or whatever in any kind of society, but now what we desperately need to understand are the mathematical expressiveness or underpinnings of such social machines, right? Because these kinds of machines are now the scale of these are worldwide, and suddenly these machines we are part of such social machines, whether we are even aware of it or not. I am part of Quora, I'm part of Facebook, and I'm not even aware of how big this social machine is, right? And how it is impacting me and so on, right? And so the need for mathematically characterizing them. See, things have always existed, right? And but our mathematical modeling of those things is what is evolving. So that's the point. Okay, thank you.
Thank you, sir. It's been a wonderful day so far with some incredible talks. Thank you to our speakers. We're now going to break for lunch. I request the faculty members and the speakers to go near room 134 down the corridor where lunch has been arranged. Students need to approach the reception desk. We'll meet again at 2:30. Thank you.